There we go. So what I want to do today is look at equilibrium in sort of a brief way, and I'm not going to cover every single piece of the chapter. We'll go through chapter 14 uh, in it, and after we cover chapter 17. But right now, what I want to do is look a little bit at the calculations that you can do for um, the the calculations that you can do with concentrations and equilibrium. And here's an example of a hypothetical reaction where I have 2 red turning into 1 blue. And you start out with only red and 0 blue. And then the concentrations change over time. Red decreases, blue increases. And what's happening is that so it continues to increase, but it increases, red decreases and blue increases at a slower and slower rate until finally it's like there is no net increase or change in concentration at about, say, 110. I guess this would be, let's say it's minutes, 110 minutes, or seconds. I guess Tro says seconds, so we'll call these seconds. So from about 110 down, there's really no change. It doesn't mean that nothing is happening. It just means that blue is turning to red at the same rate that red is turning to blue. And you can think of this as a graph. Your red come in and decrease in concentration while your blue are increasing. But as the blue increases, now the rate of blue turning into red also increases because you have more reactant. As red decreases, the rate of red turning into blue would decrease because you have less reactant. So initially, only the forward reaction happens because there is nothing to do a reverse reaction with. And as this forward reaction proceeds, it builds up more products and consumes reactants. And because of that, the forward reaction slows down. You can see the curvature in that. And the rate of the reverse reaction increases until now they reach a point at which they're equal. So eventually both reverse and forward rates become equal, and after that no net change. As long as the system is not perturbed in any way, there will be no net change in reactants or products. In concentration, however, there will be reaction happening all the time. It's not that the reaction has stopped, it's just that the forward and reverse rates are now equal. So this is an example. H2 plus I2 makes 2HI. And if you were to look at the molecules, you mix these two together, and the instant you mix them together, you have just hydrogen and iodine and nothing else. Now, after, let's say times 16, let's call this 16 seconds, the iodine now and some hydrogen iodide has formed, and you still have a lot of reactants, of course. At 32 seconds, there are more hydrogen iodide and fewer iodines than hydrogens. So now you have 1, 2, 3, 4, 5, 6, 7 HI. It looks like maybe 8. I must be missing one. 8 HI. I2 is only 1, 2, 3, 4, and H2 is 4. Now, at another later time, essentially this concentration hasn't changed. which means in between these times that the reaction is at equilibrium. Go, go, go. Don't worry. Go, go. That's fine. Lie down. So you can write these constants. Essentially, if I have a reaction, some number of B goes to some number of C, D, and DD, for example. I should have A in here somewhere. I think A is, oh yeah, A, it's up here. A plus BB goes to CC. So this is your generic reaction. The equilibrium constant is the concentration of the products C to the C times D to the D over A to the A times B to the B. When this is at equilibrium, this is the equilibrium constant. We'll see that this has values other in equilibrium, and in fact this ratio in general, whether at equilibrium or not, is called the reaction quotient Q. This will be explained later in chapter 17. We'll look at that some. What Q means and why this special equilibrium case exists from a thermodynamics perspective. So here's a typical reaction. This is the breakdown of dinitrogen pentoxide to NO2 and O2. And so there are two nitrogen pentoxides as the reactant, dinitrogen pentoxides, and those are now in the denominator squared because of the 2, and there are 4 NO2 produced, so that's in the numerator to the 4th power because of the 4, and 1 oxygen to the 1st power. And that's what KEQ will be. The equilibrium constant will be equal to this. In other words, the equilibrium constant is Q when the reaction is in equilibrium. And reactions can either go very far toward equilibrium. The bigger that K, the bigger the amount of product there is compared to reactant, the larger the amount of product. So in this case, K is 10 to the 25th. 8 times 10 to the 25th, so almost 10 to the 26th power, which means when this reacts there is very little SO2 or O2, it's entirely SO3. And you can have other reactions that don't quite go so well. For example, N2 plus 2O2 gas going to 2NO2 makes the equilibrium constant, which is NO2 squared over N2 times O2 squared, is 3 times 10 to the negative 17th, which means if you mix these together and they're in equilibrium, you'll have mostly N2 and O2 and very little NO2. So when you're thinking about K, if you consider that the reaction forward and the reaction backward are simply, they're reverses of each other, then in the backwards reaction, the reactants that were the reactants in the forward reaction become the products, and the products in the forward reaction become the reactants when the reaction goes backwards. So what that means is simply flipping the equilibrium constant upside down, and now K in the forward direction equals 1 over K in the backwards direction, or vice versa. K backwards equals 1 over K forward. So backwards and forward equilibrium constants are inversely related to each other. So you could say that if we had the reaction, say 2NO2 goes to 2O2 plus N2, this would now be 1 over 3 times 10 to the negative 17th, which is a very big number. And of course that means that there would be more O2 and N2 than there is NO2 in the reaction mixture at equilibrium. Now if you're multiplying a reaction, notice what's happening here. I have K original equals C to the C over A to the A plus times B to the B. Now if I multiply through that entire reaction by 2, now my coefficients are doubled, which means it's 2 times the power. So 2A over 2C, C to the 2C over A to the 2A times B to the 2B. So which is, of course, if you move that 2 out, it is squared. So the new is simply, if you multiply an equation by n, so take some reaction and multiply the whole equation by n, then KEQ is simply equal to the old KEQ to the n power. So if we have two reactions that add together to give a product, then the KEQ of this is going to equal, the new KEQ is going to be the product of the two KEQ for each of the reactions. So if I have K1 is equal to, so if I have here AA goes to BB and BB goes to CC, then I have K1 as B to the B power over A to the A power, and K2 is C to the C power over B to the B power. Now if I add them together, so I have AA goes to CC, it is going to be B to the B over A to the A times C to the C over B to the B. Well, these cancel out and it becomes C to the C over A to the A, which would be, if I have A going directly to B, that would be the reaction. So that's simply multiplying through by these reactions, which is multiplying the KEQ through. Compute the equilibrium constant at 25 degrees for the reaction NH3 goes to 0.5 N2 and to 1.5 NH N2. And you're given N2 goes to 3H2, N2 plus 3H2 goes to 2NH3. So if we look at this, we've got a reversal. We're essentially dividing this so we have 1 NH3 here. First of all, we're reversing the reaction, and what we might do is first figure out what that equilibrium constant would be in the forward direction. So we could say, well, if N2 plus 3H2 makes 2NH3, the reaction is 3.7 times 10 to the 8th. Now we've got a half an N2 and a 1.5, so that really means you're multiplying this reaction through by 1/2. half, which means that you would end up with 3.7 times 10 to the 8th to the 1/2 power. Now you're reversing that, so that means it is 3.7 times 10 to the 8th to the negative 1/2 power. So then you simply, that is equal to 1 over the square root of 3.7 times 10 to the 8th power. And when you evaluate that out, you end up with 5.2 times 10 to the negative 5th power. Okay. Let's see. This is sort of a jumble, but you have a reaction. A goes to 2B, it reaches equilibrium. A is 1 times 10 to the negative 5th molar, B is 4 times 10 to the negative 1st molar. When reaction 2B goes to Z, the equilibrium B is 4 times 10 to the negative 3rd molar, and Z is 2 times 10 to the negative 6th. Let me see if I can do something here. I think so. Let's get, oops. A goes to 2B, and then 2B goes to Z, now if we look at this, and you can also calculate the equilibrium constant for example, A goes to Z. So A goes to 2B is, so we have so we'll call this K1 and K2. K1 equals B squared over A equals 4.0 times 10 to the negative 1 quantity squared over one times 10 to the negative 5th. Now K2 equals, this is K2, that would equal Z over B squared, which is equal to 2.0 times 10 to the negative 6th squared over 4 times 10 to the negative third. Oh wait, actually it's not squared. Sorry about that. It's not squared. 2 times 10 to the negative sixth over 4 times 10 to the negative 3. That is squared. So the total equation, which is a goes to z, should equal, let's get rid of that squared, just scribble it out. So it should equal 4 times 10 to the negative first squared over 1 times 10 to the negative fifth times 2 times 10 to the negative sixth over 4 times 10 to the negative third squared. And this is going to give us the total KEQ expression. So that would be the total KEQ. So we could evaluate that out, and let me go ahead and put that up here. We have 1.6 times 10 to the negative 1 over 1 times 10 to the negative fifth times 2 times 10 to the negative sixth over 1. It would be 16 times 10 to the negative 3 plus negative 3, which would be negative 6. So it's 1 times 10, 1.6 times 10 to the negative fifth. So that would be how we would evaluate that. You could just run through and evaluate that expression then. I'm not going to go into the gas laws as such, but what I wanted to talk about was more, well, heterogeneous equilibrium. If you think about this, if you have a solid in equilibrium with something else, like gas, then the amount of solid really doesn't matter. Here you have carbon in equilibrium with carbon monoxide and carbon dioxide, and 2CO goes to CO2 plus C is what the idea. And it's not going to matter how much carbon you have, because only the carbon on the surface will actually react. In order to be involved in the equilibrium constant, it has to be in a homogeneous solution. And the other thing is the solvents are not included in the equilibrium constant. So water, if it's done in an aqueous solution, would not be included in the equilibrium expression. So here we have a reaction. KNO3 plus H2O makes HNO2 plus H2O makes H3O plus NO2 minus. So H3O and NO2 minus, there's one of those, it's on the top, no coefficient. HNO3 is on the bottom. H2O doesn't get included. CaNO3 plus H2SO4 makes CaSO4 solid plus 2 HNO3. Again, here is a case where you have a solid that is not included in the products part. HNO3 is the only one that is in the products part, so it's HNO3 squared. CaNO2 and H2SO4 and CaNO3 and H2SO4 are all in solution, so they're okay. They're in the bottom. Okay, well, I'm going to take a look at some problems that I said that I was going to look at some problems that are similar, and these are using what's called the ice plot. Well, look at initial concentrations and then equilibrium, and look at how basically use stoichiometry to show what is made and what is consumed, and then you can calculate from that an equilibrium concentration, and from that then you can calculate the equilibrium constant. So and this is really what we did in the lab, so this is really the direct way of calculating equilibrium constant. So here is a case where you have initial concentration of H2 and I2 reacting to make HI, 2HI. So the equilibrium expression is HI squared. Well, we can measure one of these made. So let's say we measure the HI. The HI is 0.78, which means that it was taken away then for each 2 HIs that are made, one H2 and one I2 is consumed. So you have, starting out with 50, you have of course at the beginning 0, and now you have 0.1 and 0.11. Well, you take 78 over 2. So let's see, 70 is 35, so that would be half of 70 is 35, half of 8 is 9, so that would be 39, or 0.39. So let's see, this would be 50 minus 0.39, well, or 0.50 minus 0.39 in this case. 0.50 minus 0.39. That means that you've got, now subtracting that 0.39, you get 0.11 and 0.11. This is your equilibrium concentration. So you have a change of 0.39, for each of the initial ones, a change of negative 0.39, a change of plus 0.78 for the HI, and then you get this equilibrium concentration. 0.78 squared over 0.11 times 0.11 is going to equal 50. Now suppose you started with all HI and it went backwards. It doesn't matter. At the equilibrium, you're going to end up also, it will, the equilibrium constant will be the same regardless of your initial or concentrations. Okay, so 0.50 over 4 is going to be 0.125, and then for A that means 2A are consumed for every 4, so 0.125 times 2 is 0.25. So you take 0.25, subtract it from 1, you get 0.75. You take 0.125 from 1 and you get 0.88. And then when you have knowing just one of these in equilibrium, if you know the starting concentrations and one of these in equilibrium, if you have the stoichiometric relationship, you can get the others. And now KEQ is simply going to be 0.50 to the fourth over 0.75 squared times 0.88. Okay. Let's take a look at this one. We have CH4 going to C2H2 and 3H2. This is something that's happening at like 1700 degrees. And our initial concentration of CH4 is 0.115 molar. And the equilibrium concentration of C2H2 is 0.035. Oh, it's making 3H2 as well. So we can figure that. So if I have 0.115 to start out with, we have no C2H2, no H2. Now we're adding 0.35 to that. Well, notice we have two of the CH4s making one C2H2. So that means that twice this much will have had to be consumed, which means that 0.070 that's being consumed. So this has to be negative 0.070. Now the H2 is 3 times the amount of C2H2 that's made. So now you have a plus, well, what's 3 times 0.0035? 0.07 plus 0.0035, right? That'd be 0.1. That's 10, so 105. So this would be a plus 0.105. That's minus 0. That's not a very good. Minus 0.70, And now we take 115 minus 0.70, so we have 0, 11, let's see, 11 minus 7 is 4, so that's 4. So it's 0.0, that's 5, 4, 5, 4, CH4. And this is 3, 5, and of course this is 0.105. So we could calculate then KEQ equals 0.405. That would be on the bottom, and that would be squared, and on the top you have 0.035 times 0.105 to the third power. That would give you your KEQ. And total then being 0.020. So let's see, now we have 2NO makes N2O4. This is a classic equilibrium constant problem. This is a type of thing where under some conditions you have this brown material, NO2, and change the conditions slightly, it turns to a clear N2O4. So let's see, now we have an initial concentration of 0.02 NO2, no N2O4. Our equilibrium concentration of NO2 is 0.0172. Well, for every two of these made, there is one of these made, so we take the change, 0.02 minus 0.172 is 0.0200 0.0172. Well, that would be like 0.28, right? So this would be then negative 0.28. And now half as many of the N2O4 as NO2 are consumed, so that's an plus 0.0014. So now our concentrations at equilibrium would be 0.127 and 0.0014. 0.0172 I mean, and 0.0014. So we could write the KEQ. Kc means concentration as opposed to pressure. I'm not going to worry about the pressure because we haven't really covered that yet. Kc is going to be 0.0014. That's the product over 0.0172 to the second power. And that extra ends up being, well, it's not this one, that's Kp. This is it. Kc is 0.47, or 4.7, sorry, 4.7. Okay. So the reaction quotient is something that I had mentioned. The reaction quotient is simply Q at whatever concentrations you have. And Q is simply the KEQ is simply Kc when you get to equilibrium. So if Q is greater than K, your reaction runs backwards. If Q is less than K, the reaction runs forward. So here's predicting a reaction. You have pressures which you use exactly the same as concentrations. If you're given the KEQ, Kp is 81.9. So we have I2 plus Cl2 going to 2ICl. And we can take the pressures and put them into the reaction quotient. So you're simply taking the pressures that are given to you, which is so we've got essentially ICl squared, right, over I2 times Cl2. So Q is, you put the 0.0355 atmospheres in, square it, and then you put the 0.114 atmospheres and the 0.102 atmospheres in the bottom, and you get 10.8. Well, what is KEQ? Or the Kp is 81.9, so clearly it will go in the forward direction because Q is less than KEQ. Okay, I'm going to stop here because we really aren't using this in the lab, calculating equilibrium concentrations from the equilibrium constant. We are going the other way, and we'll get to this after we're done with thermodynamics. I hope this helped. I apologize for some of the extraneous noises, but I hope this can helps you go understand equilibrium a little bit more. Okay. Thank you.